Lesson 4.2 covers an introduction to linear programming. In the previous lesson, we were labeling our solution area with the word solution. This area consists of all the possible solutions for a particular problem. Well, all the values in that area were possible or feasible. So now, since we're introducing linear programming, we're going to call this area the feasible solution area and just label it FSA for short. Well, often some of the possibilities are better than others, and we actually often want what we call extreme values. When we have a feasible solution area, the corner points always represent the extreme values. For instance, if a system has a maximum or a minimum solution, it will be a corner point. Well, a linear programming problem is one in which you wish to maximize or minimize an objective function. In a previous lesson, we looked at an example where a lady was investing in stocks and bonds, and she had lots of investing possibilities. Well, generally, you don't want to just invest. You invest for a purpose. So she was probably wanting to invest to maximize her income or to maximize the return on her investments. So that would be a maximize problem. There'll be some examples where we're talking about cost and we want to find the minimum cost. So we want to minimize our cost. That would be a minimize problem. And when we're looking for these solutions, we have several possible solutions, but the values that give us the maximum and the minimum will be our corner points. Let's look at this example. I want to find the maximum and the minimum values for the objective function z equals x plus y, subject to the feasible solution area below. Now, for simplicity, I haven't shaded this graph. But if you notice this quadrilateral right in the center, it's labeled FSA, so that's my feasible solution area. Corner points are where two of your constraints cross. So these two first constraints cross at the point 2,5. These two constraints cross at the point 7,5. Then I have a corner point at 3,2 and a corner point at 6,2. As I said, corner points are 2,5, 7,5, 3,2, and 6,2. The corner points are formed when two boundary lines cross or intersect. To find out which corner point gives us our max and which gives us our min, I plug these values into my objective function. So my objective function was z equals x plus y. So for the first corner point, I plug a 2 in for the x and a 5 in for the y, and I get 2 plus 5 is 7. For my second corner point, I have 7 plus 5 is 12. Then 3 plus 2 is 5. And finally, 6 plus 2 is 8. Well, if I look at the values that my objective function gave me, I have a 7, a 12, a 5, and an 8. The biggest is my 12, so that gives me the max. The smallest is the 5, so that gives me the min. So the way we word these is you tell me the function has a maximum value of 12 at the point 7,5, and the function has a minimum value of 5 at the point 3,2. This is the way you need to word your answers when you're doing the homework and then when you enter them on the quizzes and the test. So now let's look at an example and go all the way through. This is going to combine graphing the inequalities that we did in the last lesson with finding the maximum and minimums that we just covered. So I want to find the maximum and minimum values for the objective function z equals 18x plus 30y, subject to the following constraints. So I begin by graphing each constraint. For each constraint, I want to find my boundary line, find my intercepts, use a test point, and then shade my graph. Well, first note, since all of the inequalities have the equal to signs, all are going to be solid boundary lines. If I begin with the first boundary line, 2x plus y equals 8, my x-intercept, I let y be 0, and I get 2x equals 8. If I divide by 2, I get x equals 4. So my x-intercept is the point 4, 0. For my y-intercept, I let x be 0, so I end up with y equals 8. So the y-intercept is 0, 8. Then my second boundary line, I have x plus 2y equals 10. For the x-intercept, let y be 0, and I end up with x equals 10. So I have the ordered pair 10, 0. For the y-intercept, let x be 0, and you end up with 2y equals 10. If you divide by 2, y equals 5. So you have the ordered pair 0, 5. And then finally, 5x plus 4y equals 20. For the x-intercept, let y be 0. So you have 5x equals 20. If you divide by 5, x equals 4. So you have the ordered pair 4, 0. Then for the y-intercept, let x be 0. So you have 4y equals 20. If you divide by 4, you get y equals 5. So I have the ordered pair 0, 5. So let's begin with the first inequality. The boundary line was 2x plus y equals 8. It was a solid boundary line, and then I had the intercepts 4, 0, and 0, 8. So graph your intercepts of 4, 0, and 0, 8. Draw a solid boundary line through those. Since this is the first boundary line, I suggest you writing a 1 beside that, because we're going to have 3 lines graphed, and sometimes we may need to go back and look at which line is which. So it's just helpful to put a little 1 beside it to know that was your first boundary line. That does not go through 0, 0, so my test point can be 0, 0. If I test 0, 0, go to the original inequality with the less than or equal to 8. If I plug in 0, 0, I get 0 is less than or equal to 8, and that's true. So since 0, 0 was true, every point below the line is true, so every point above it is false. So I mark out my false area. So I'm going to shade above the line. Now look at your second boundary line, x plus 2y equals 10, and this was also a solid boundary line. So graph the points 10, 0, and 0, 5. And draw a solid boundary line through those. Since this was my second boundary line, I label it with a 2. Since that boundary line does not go through 0, 0, I can test 0, 0. So use your original inequality, the less than or equal to 10, and if I plug in a 0, 0, I get 0 is less than or equal to 10, which is true. So for line 2, 0, 0 was true. So below the line is true, above the line is false. So mark out or shade the false area. So you're going to shade above the line. Now graph your third boundary line, the 5x plus 4y equals 20. It's a solid boundary line also. The x-intercept was 4, 0, and the y-intercept was 0, 5. And then draw a solid boundary line through those. Since this is your third boundary line, label it with a 3. Since this line does not go through 0, 0, I can test 0, 0. My original inequality was 5x plus 4y is greater than or equal to 20. So if I plug in a 0, 0, I get 0 is greater than or equal to 20. That's false. So this time for line 3, 0, 0 is false, so everything below the line is false. So I'm going to shade below the line. So for your final answer, look at the area that has no shading in it, and that's the triangle that's formed between all the lines. That's my feasible solution area, so I'm going to label it FSA. This is a bounded region because it's completely enclosed by boundary lines. Now I want to list the corner points. Well, 2 of my corner points are intercepts. I have the point 4, 0. I have the y-intercept 0, 5. And then my third corner point is where 2 of my boundary lines intersect. This is where it's helpful to know which lines those were. If I start at my corner point and trace back the lines, it was line 2 and line 1. So my third corner point is formed by the intersection of lines 1 and 2. Now by looking at my graph, that looks like the point 2, 4. But don't ever go by the graph. Always find this using the elimination method. So I want to find the intersection of lines 1 and 2. Line 1 was 2x plus y equals 8. Line 2 was x plus 2y equals 10. So if I think of that as a system of equations, I'm going to use the elimination method. So I can eliminate either the x's or the y's. With both of them, I'm going to get the numbers in front, the coefficients, to be a 2 and a negative 2. So if I eliminate the x's, I would multiply the second equation by a negative 2. To eliminate the y's, I would multiply the first equation by a negative 2. And it doesn't matter which one you do. I'm just going to eliminate the y's, so I'm going to multiply the first equation by a negative 2. And when I do this, I get negative 4x minus 2y equals negative 16. Then if I add the second equation to that, I have x plus 2y equals 10. Well, negative 4x plus x is negative 3x. The y's eliminate like I wanted them to. And negative 16 plus 10 is negative 6. Now to solve for x, divide each side by negative 3 and you get x equals 2. So take that x value and plug it into either one of the equations. So if I go back to the 2x plus y equals 8, x is 2, so I have 2 times 2 plus y equals 8. This gives me 4 plus y is 8. If I subtract the 4, I end up with y equals 4. So my third corner point was the point 2, 4. So list the point 2, 4 with your other 2 corner points of 4, 0 and 0, 5. Now to find my maximum and minimums, I take each of these corner points and plug them into my objective function. The objective function was z equals 18x plus 30y. So I just listed my corner points. If I plug in the 4, 0, I get 18 times 4 plus 30 times 0. And this gives me a 72. Then if I plug in the 0, 5, I get 18 times 0 plus 30 times 5, and this equals 150. And then finally, if I plug in the 2, 4, I have 18 times 2 plus 30 times 4, and this gives me 156. So looking at your values for z, the largest one is 156, so that's my maximum. The smallest value is 72, so that's my minimum. So you always tell me what the maximum or the minimum value was and at which corner point it occurred at. So the maximum value is 156 at the point 24. We have a minimum value of 72 at the point 40. In the next example, I want to find the maximum and minimum values for the objective function z equals 10x plus 2y. And then I've got the following constraints. I have x plus y is greater than or equal to 7. 8x plus 5y is less than or equal to 50, and then x and y are both greater than or equal to 0. Let's begin by just noticing that both of our boundary lines are going to be solid. So now let's graph each boundary line. The first boundary line is x plus y equals 7. For my x-intercept, let y be 0, and I end up with x equals 7. So this gives me the intercept 7, 0. For the y-intercept, you let x be 0. If x is 0, I end up with y equals 7, so I get the intercept 0, 7. Then I have 8x plus 5y equals 50 as my second boundary line. For the x-intercept, let y be 0, so you get 8x equals 50. If I divide each side by 8, I get 50 over 8. Don't make that a decimal, just leave it a reduced fraction, so you get the intercept is 25 over 4, 0. Then for the y-intercept, let x equal 0. If x is 0, we get 5y equals 50. And if I divide each side by 5, I get y equals 10. So my y-intercept is the point 0, 10. So now we're ready to graph these boundary lines. First, begin with the restrictions x and y are greater than 0. That means there's going to be no negative x or y values, so we're using quadrant 1. So we can shade or mark out all other quadrants. Next, let's graph x plus y equals 7. So I have the intercepts 7, 0 and 0, 7. And I'm going to draw a solid boundary line through these and label that boundary line as line 1. Now this boundary line does not go through 0, 0, so I can test 0, 0. Go back to the original inequality, x plus y is greater than or equal to 7. And if I plug in 0, 0, I get 0 is greater than or equal to 7. And that's false. So that means 0, 0 tested false, so every point on the same side as 0, 0 will be false. So we shade or mark out our false area. So we're going to end up shading below that line. Our next boundary line, we had the intercepts 25 fourths, 0, and 0, 10. With the fractions, just estimate those. 25 fourths is 6 and 1/4. So just graph the intercept a little bit past 6. And then I have the intercept 0, 10. We'll draw a solid boundary line through these, and this is our second line, so we label it with a 2. This line also does not go through 0, 0, so I can test 0, 0. Go to the original inequality, 8x plus 5y is less than or equal to 50. If I plug in 0, 0, I get 0 is less than or equal to 50. And this time it's true. So the side of the line with 0, 0 was true, so the other side is my false side. So mark out or shade your false side. So that leaves me with a triangular feasible solution area. So we want to begin by listing our corner points. The first corner point was at 0, 7. The second corner point that's also an intercept is at 0, 10. And then I have a third corner point where the two lines intersect. So this third corner point is formed by the intersection of lines 1 and 2. This looks like the ordered pair 5, 2, but don't ever go by the graph, especially since we estimated this intercept right here that was a fraction. So always find the intersection of the two lines using the elimination method. So line 1 was x plus y equals 7, and line 2 is 8x plus 5y equals 50. If I multiply line 1 by -8, I could eliminate my x's. Or if I multiply line 1 by -5, I could eliminate my y's. And it doesn't matter which one you do. I multiplied the first one by -5 just to keep the numbers smaller. And when I do this, I get -5x minus 5y equals -35. Then recopy line 2, or the second equation, 8x plus 5y equals 50. When I add these together, -5x plus 8x gives me a 3x. The y's eliminate like we wanted them to, and -35 plus 50 is 15. Then if you divide each side by 3, you get x equals 5. Now take your x value and plug it into either equation for line 1 or line 2. I'm just going to use my first one, the x plus y equals 7. If I plug in a 5, I get 5 plus y equals 7. Now subtract 5 from each side and you get y equals 2. So our third corner point is the point 5, 2. Be sure to always list the x first. So if I add this to my list of corner points, I have my corner points are 0, 7, 0, 10, and 5, 2. I plug each of my corner points into my objective function, which was z equals 10x plus 2y. If I plug in the 0, 7, I end up with 10 times 0 plus 2 times 7 equals 14. If I plug in the 0, 10, I have 10 times 0 plus 2 times 10, and that gives me 20. If I plug in the 5, 2, I have 10 times 5, which is 50, plus 2 times 2, which is 4, and 50 plus 4 is the 54. Now that we have our values of the corner points plugged into the objective function, the smallest one, which is 14, is our minimum, and the largest, which is 54, is our maximum. So we have a minimum value of 14 at the point 0, 7, and we have a maximum value of 54 at the point 5, 2. And on the test and quizzes, you're going to have to tell me what the minimum and maximum values are and which points they occur. So let's look at the final example. I want to find the maximum and minimum values for the objective function z equals 3x plus 7y, subject to the following constraints. I have x plus y is less than or equal to 6, 2x plus y is greater than or equal to 6, y is less than or equal to 2, and then x and y are both greater than or equal to 0. So I want to begin by listing my boundary lines and finding the intercepts so I can graph them. And before I do that, I just want to notice that all my boundary lines again are solid. So my first boundary line is x plus y equals 6. For my x-intercept, let y be 0, so you get x equals 6. So I have the x-intercept as the point 6, 0. For the y-intercept, let x be 0. So I end up with y equals 6, so I have the ordered pairs 0, 6. My second boundary line is 2x plus y equals 6. So for your x-intercept, let y be 0, and you have 2x equals 6. If you divide each side by 2, you get x equals 3, so we have the x-intercept as the point 3, 0. For the y-intercept, let x be 0. If x is 0, you have y equals 6, so we have the y-intercept as the point 0, 6. If you notice, your third constraint is just y is less than or equal to 2. So my boundary line is y equals 2. Since there's no x value, This is a horizontal line passing through the y-axis at 2. So I don't have to find my intercepts because I know this is a horizontal line since my only variable is a y. So let's begin with the two constraints x and y are greater than or equal to 0. We know that these tell us there will be no negative x or y values, so we're limited to quadrant 1. So you can shade or mark out all other quadrants. Then next I want to graph the boundary line x plus y equals 6. Well, my intercepts were 6, 0, and 0, 6. And this was a solid boundary line. So I'm going to label it with a 1 since it was my first line. Since that does not go through 0, 0, I can test 0, 0. So I go back to my original inequality, x plus y is less than or equal to 6. If I plug in 0, 0, I get 0 is less than or equal to 6. This is true, so that means 0, 0 is true. So every point below the line is true, then every point above the line is false. So I shade or mark out my false area. Now my second boundary line is 2x plus y equals 6. So graph those intercepts 3, 0, and 0, 6. 0, 6 was already the y-intercept for my first equation, so it's already graphed. And then draw a solid boundary line through those intercepts and label it line 2. That boundary line does not go through 0, 0, so I can test 0, 0. So go to the original inequality, 2x plus y is greater than or equal to 6. If I plug in 0, 0, I get 0 is greater than or equal to 6, and this is false. So since 0, 0 tested false, I'm going to shade below line 2. I'm going to shade the side with 0, 0 or mark out the false area. Then my third boundary line was the horizontal line at y equals 2. So find 2 on your y-axis and draw a horizontal line through it, and we'll label this 3 because that was my third boundary line. I can test 0, 0 because that line does not go through 0, 0. So go to your original inequality, y is less than or equal to 2. I only have a y, so I'm going to replace it with 0 and get 0 is less than or equal to 2. That's true. So 0, 0 was true, which means I'm going to shade above the line. That's my false area that I'm marking out. So now I have a four-sided region that's my feasible solution area. It's enclosed all the way around by boundary lines, so this is a bounded solution. Now I want to find my corner points. Well, I've got two corner points at my intercepts. I have the intercept 3, 0, and I have the intercept 6, 0. Then I have two other corner points. The third corner point, if you trace back, and this is why I label the lines, that's formed by the intersection of lines 2 and 3. My fourth corner point is formed by the intersection of lines 1 and 3. Let's look at the intersection of lines 2 and 3. Line 2 was 2x plus y equals 6, and line 3 was y equals 2. So you can think of these as being a system of equations to solve. We normally solve these with the elimination method, but since the second one was a horizontal line, it's already solved for y. I know that y equals 2. Now I just need to find my x. So I'm going to take this y value and plug it into my first equation. So if I take the 2x plus y equals 6, I'm going to replace the y with a 2. And this gives me 2x plus 2 equals 6. If I subtract 2 from each side, I get 2x equals 4. And then finally, if I divide by 2, I get x equals 2. So my third corner point is the ordered pair 2, 2. Now let's look at the intersection of lines 1 and 3. Line 1 was x plus y equals 6, and line 3 was y equals 2. So you can think of these as a system of equations. And again, since the second one is a horizontal line, we already know the y value is 2. So we just need to find our x. If I take my first equation, the x plus y equals 6, I can replace the y with a 2, and I end up with x plus 2 equals 6. Then if I subtract 2 from each side, I get x equals 4. So my fourth corner point is the point 4, 2. Be sure to always put the x first. So let's go back to our list of corner points. I have 3, 0, 6, 0, 2, 2, and 4, 2. I'm going to plug each of these into my objective function, which is z equals 3x plus 7y. So if I plug in the 3, 0, I get 3 times 3 plus 7 times 0, which is just a 9. If I plug in the 6, 0, I get 3 times 6 plus 7 times 0, which is 18. If I plug in the 2, 2, I get 3 times 2, which is 6, plus 7 times 2, which is 14, and 6 plus 14 gives me 20. And then if I plug in my 4, 2, I have 3 times 4, which is 12, 7 times 2, which is 14, and then if I add the 12 and 14, I get 26. So now that I have all my values for the objective function, the smallest one is my minimum, and the largest one is my maximum. So we say we have a minimum value of 9 at the point 3, 0, and we have a maximum value of 26 at the point 4, 2.